Well, welcome everybody. I'm so glad you're here. My name is Jay Egg. I'm with Egg Geo. We're so grateful to IAPMO, the International Association of Plumbing and Mechanical Officials. The Radiant Professionals Alliance made this possible, and we're grateful to those guys. We're grateful to IGSHPA, which is a huge advocacy group for geothermal implementation. We've got the president of IGSHPA here today, Courtney Lowell. Say hi, Courtney. Don't bother her, though. She's really busy. She's trying to run a business at the same time. I say that with all the love in the world because we know what that feels like. So what we're going to talk about today is right here. Geothermal coupled piped infrastructure upgrades are balancing our energy budget. Now that's a big old mouthful. So let's talk a little bit about what I'm going to try to get across today for everybody that wants to take a little bit of a deep dive with me. So infrastructure, in this case, simply means we're tying together thermally a bunch of buildings in a community or a city or whatever, whether it's a brownfield or a greenfield. It's just about tying together a bunch of buildings thermally. And when we talk about, that's the piped infrastructure, when we talk about balancing our energy budget, what I want you to think about here is, as we're electrifying the grid, the number one complaint you hear is, how are we going to handle all of that heating electricity? What was heating from before the age of decarbonization, or what we're planning? Heating is from combusting fuels. So if we have a winter where our electric utilities are typically idling now because we're using natural gas typically to heat our buildings, what is going to be the new source of heat? We all know what that is, right? It's electricity. Now, there's several ways to make electricity the heat source for a building. You can either burn kWs, meaning 1 kilowatt of electricity gives you 1 kilowatt of heat, or you can use another piece of equipment to absorb heat from other sources, and we're going to talk about that, and pump them into buildings. And those are called heat pumps. So we're going to talk about the different types of heat pumps that we use to help balance our energy budget. So we'll talk a little bit more about this, that drawing a little bit later in our presentation. What I want to focus on right now is these two drawings right here. They're kind of like flow charts, and I think I have a better one right here. It's a little more colorful. So if you think about the U.S., you may not know this, but there are about 2.5 million miles of natural gas pipe infrastructure in the earth right now that supply natural gas services for about 85 million people. So if you consider a natural gas pipeline, you get the pipe in the ground supplying natural gas to a furnace or boiler, which combusts that at about 95% efficiency to provide heating, domestic hot water or space heating. Now, if you consider a geothermal or a thermal energy network, a pipe in the ground like you see here, the infrastructure is the same. That's what I want you to notice more than anything. The infrastructure is the same. The utilization technology differs only in what it does. They kind of look the same. A furnace that provides heated air to a building looks very similar to a heat pump. So, and the same thing could be said for a boiler or a chiller heat pump. Either way, the heat pump or the furnace boiler, and in this case, the heat pump can provide heating and cooling. The difference is the energy source is not from some other source in another state or another town. The energy source is all local. It's all the local energy. And the cool thing about a thermal energy network is some of the buildings are actually cooling dominant, where they're putting heat out into the loop even when it's cold outside, especially data centers and the like. And then your residential structures that need the heat are able to absorb the heat from a thermal energy network. So as we consider this, I'd like to just give you an idea. Here's an example of a town that decided to replace, while they were doing new water lines in the town, they decided to do a thermal energy network. It's a perfect example, right? If you're going to be tearing up the streets anyway, and you're piping water, it's an excellent time to consider a thermal energy network. This is an example of when they built the World Trade Center in New York City. They wanted to minimize the use of cooling towers. So what did they decide to use? It's called surface water geothermal exchange. Kind of like we're talking to some of our friends about doing something like that in Chicago. And the surface water, they use 442-inch lines to circumvent the use of cooling towers so much. They were able to pump some of the heat into the river. So this is an example of a distributed geothermal resource with what we call a twin T here. Basically, it's a decoupled secondary circuit that provides heating and cooling through the use of a condenser water loop into the building. So as we look at our aging infrastructure, what we're talking about is trying to replace the infrastructure that's aging with something that's going to be useful. And the aging infrastructure, this is where it really started, because where it really started is in Massachusetts, when the local utility asked for $9 billion to replace aging infrastructure in the natural gas pipelines. A group called the Home Energy Efficiency Team, HEAT, went ahead and decided to challenge that, saying, shouldn't we be putting in something that enables non-combustion heating? And they started doing some good. So a lot of what we're talking about here has to do with that. Now, sorry to jump over to this, but I wanted to point this out lest I didn't get a chance to really illustrate the genius of thermal energy networks. This is an actual project going in Manhattan, and in this case, these 15 22-story buildings, which encompass 5 blocks in the Chelsea district of Manhattan, need about 4 megawatts of thermal energy. They have a 4 megawatt boiler to provide enough heat for these 2,500 families to make it through a cold winter day. So the genius of considering a thermal energy network is there's one reason we're doing all this, and that is to be able to turn off boilers and furnaces. And in order to turn off the boiler here, we have to get 4 megawatts of thermal energy into this complex. Well, companies or state agencies like NYSERDA are commissioning companies to go in and try to figure out where to get this energy from. You can get it from boreholes, which is great. In other words, geothermal boreholes to pull it from the ground. Or you can, and this is the genius of thermal energy networks, you can talk to some of the neighbors, like the U.S. Postal Service here, which has their main distribution station for Manhattan. And they expend about 8 megawatts of thermal energy through their cooling towers. So we just have 2 entities that are not communicating thermally here. So by doing this pipeline from here into the central energy plant here, that 8 megawatts of thermal energy, they can turn off the cooling towers, pipe that thermal energy into the pipeline between here and there, which is proposed right now, and simply replace the 4 megawatt boiler with a 4 megawatt heat pump. A 4 megawatt heat pump will use, as most people understand from COPs, it'll use about 1/3 to 1/5 the energy of direct electric resistance heating. So the reason there are other entities tied in here is because the State University of New York has gotten involved. There's others indicated here. And the beautiful thing is, make no mistake about it, there will always be, in a built environment, cooling dominant buildings that can share heat with the other buildings in the network. In the middle of the summer is when we're going to have the biggest problem getting rid of the heat. As anybody who's ever done, such as Kelly's company, anybody who's ever done geothermal closed loop boreholes understands a lot of the time the biggest problem is getting rid of the heat. So this is always going to be a concern where we're going to try to get rid of more heat than sourcing heat, especially in these types of situations. This has become so popular that the unions, the pipe fitters and plumbers unions in the United States nationally have embraced thermal energy networks and geothermal technologies as a way to circumvent or to help, I should say it this way, as a way to decarbonize and electrify buildings. A union organization, the union in the United States, instead of crying and screaming because they're losing their jobs for their Boilermakers, they're losing their jobs for their natural gas pipe fitters, their steam fitters, they're not crying the blues. They see a huge market here. They see this as an opportunity likened to the natural gas rollout in the 50s and 60s, where we put the 2.5 million miles of pipe in the ground. They see this, and that's exactly what's going on here. Over the next 30 years through 2050, our metropolitan areas and our greenfield developments are going to be seeing more and more like we're hearing about. Maybe you're not hearing about it, but there are mixed-use communities going in at a rapid pace that are thermally linked, in other words, using thermal energy networks. So this is something that the unions have hung their hats on, so much so they got so involved. This is a senator, a state senator, speaking. This is Rich Benkowski over here on the right, who is retired national director of training, I believe, at the unions. And they're all talking about this. By the way, this state senator got a huge geothermal bill passed in Colorado while he was there. He's running for the mayor of Denver, I believe, right now. So the reason I have this slide is because this is the national director, business manager for the unions. We're in the NYSERDA building in New York because after touring in February, about a year ago right now, Christy, we walked through the Empire State Building, we walked through the Penn South, we walked through NYIT, we walked through all of these buildings. John flipped. He immediately took it to the legislature, worked with the green advocacy groups in the state of New York, and got the Thermal Energy Networks and Jobs Act passed and signed by Governor Hochul on July 5th last year. That's basically a $1 trillion bill. It's worth about $1 trillion in upgrades to the infrastructure of the state of New York over the next 30 years. And what it requires, it does two things, and this is why this is so important. It does two things. One, it allows utilities to sell thermal energy. Why is that a problem? We sell steam, right? And that's the number one thing people think. Why is this so hard? It is actually a lot more difficult than most people think of, and a lot of utilities can get by it by using ESCOs and private entities, but they wanted to get it from the PSC. And here's the thing. When you make steam, you burn natural gas. When you make geothermal for thermal energy networks, you're not using any energy, you're not burning any fuel, so they can't sell something they don't burn. And that's how they did it. They made the Thermal Energy Networks and Jobs Act, which allowed the utilities to sell BTUs. They don't care where it comes from. They don't care if you're buying BTUs coming into your building or paying for them to take BTUs going out. They can charge whatever way they convince the PSC works for the utilities. So the other thing, there are three things that I'm going to mention. The other thing, so we have a way to monetize the use of renewable energy in thermal energy networks now. The second thing is they needed teeth. And teeth means they needed a law that forced, through the PSC, the utilities to do pilot projects so they could learn how to do this and figure out how to monetize it. So that's the second thing. Every regulated utility in New York has to do at least 3 pilot projects. And They're variable depending on the size, but there are billions of dollars tied up in that too. And then the third thing is it requires a living wage. It requires that on projects that are large enough that they hire union labor, and on projects that are smaller that they pay a living wage. So those are a few things that really set a precedent. And right after getting this passed in New York, Senator Klobuchar had us help with some federal legislation, and hopefully that will go through because that's worth a lot of money for each state. So the way we really got recognized on this, and the way that thermal energy networks really got recognized. So this is interesting because this is what really kicked it off. This is now $100 million in 2017 is probably worth $250 million now, but they had a CHP project in 2017 that was funded by the state of New York. Now a CHP stands for combined heat and power, and it means that they are burning fossil fuels to create electricity or something like that, maybe just to create thermal energy, and they're using the waste heat for a good purpose. The fact of the matter is, Bill Nowak, who was with New York Geo, told me about this, and I immediately wrote an article about it, and I said, no, they should probably go to heat pumps. And we were able to ally with several different people in the state, and the bottom line is that they changed it and electrified the plaza rather than putting in a CHP, which was the beginning of things really starting to change in New York. This is part of our legislative action that got the recent bill passed. I didn't realize how big this was getting until I got a call from a reporter at Standard & Poor's, their investment portfolio. Washington Post has done articles on heat. I've seen my colleagues quoted in everything from the New York Times to the Boston Globe. This is taking some real front seat action right now. So the basics are, I want to go back to the basics before I finish, lest anybody has not been through this. We're talking about a heat pump. A heat pump is either typically air source, which we're very familiar with these. They're a very good product that has operated well for decades, and they are subject to the outside air. They take in the middle of the winter, they take the heat out of the outside air, and they're able to compress it using the Carnot refrigeration cycle and create heat. And there are claims, and the science is sound, that down to minus 22, they can create heat. The COP is the question of the efficiency. A geothermal heat pump is replacing the outside condenser with this underground component, the ground loop. So that's why it operates at the same energy consumption in the summertime or the wintertime, because it's using what is an average temperature in the United States is 55 or 60 degrees year-round as a heat source and a heat sink, versus in the summer it might be 90 or 100 outside, which makes it harder to cool, meaning it uses more energy, or it might be below freezing outside, which makes it harder to heat, so it uses more energy. So that's why we are talking about the geothermal solution. And even in a singular aspect, a lot of people don't realize, so I love this slide, it helps me to remember why we're doing this. And it isn't just, although it's about decarbonization and electrification, some people don't think about the fact that there is no more outdoor equipment to replace. The systems are more hurricane and storm resilient because there's nothing outside. The system longevity goes up by a factor of 2 or 3 times because of no equipment outside. It wears out less, it lasts a lot longer, just like an indoor garage-kept car. There are no combustion boilers or cooling towers or furnaces. There's noticeably superior comfort in heating and cooling. Remarkable system efficiency at standard pricing. We were talking about this just before we came in. It's just a heat pump. It doesn't matter whether it's water source. You can buy a water source heat pump that costs $20,000, or you can buy one that costs $3,000. It depends on your taste and what you need, and that's the beautiful thing about this. I want to point this out because this is the AHR building in Atlanta, the headquarters. This is the point. On the first floor, they used the very best VRF equipment they could get their hand on in 2010, and on the second floor, they used two-stage geothermal heat pumps. The peak energy consumption per square foot in the summertime is right here, and you can see the geothermal has a margin better than the air source, which is to be expected because it's probably 90 degrees outside. But this is what the point is. We hear about the grid crashing and things, the worries about the energy consumption in the wintertime. This is what the air source heat pumps were doing, the best the industry had to offer only 13 years ago in the air source arena. And you can see they're well over 2, if not 2.5 times the energy consumption of the geothermal. And that's not their fault. They're not dealing with the same energy heat source and heat sink. They're dealing with outside air. How can you expect? It's not even a fair comparison. People say, well, you're being mean to the air. No, it's just thermodynamics. It's warmer in the earth, and so it's going to perform better. But what the point is this solves the wintertime electrification crisis. There is no peak above the summer peak in the wintertime. And this is an actual tale of 2 buildings in Oklahoma, and this is the actual energy peak demand. Can you believe the difference in here? And look at this geothermal system here. Look at how it's just meandering along like as if it doesn't even recognize there's a difference in temperature compared with the geothermal system. And this is a National Grid slide where they showed that that right now they are peaking dramatically on electricity, and in the wintertime, of course, they're peaking dramatically on natural gas. What they're looking forward to is averaging their load, because that maximizes their funding opportunity on their electrical power plants. So it makes the electrical power plant a much more efficiently operating piece of equipment. Because I love to share this slide. I talked about the electric resistance heating, and this is very important for the basics of this. 1 kilowatt of electricity equals 3,412 BTUs. And that's just basically 1 kilowatt of electricity is a 1,200 watt heater, or 1,000 watt heater, and it's not uncommon to have a 1,200 watt heater. And so this kind of gives you an idea of what 1 kilowatt of electricity can do here. But if you take that 1 kilowatt of electricity and you power a geothermal heat pump with it, it is a heat pump, and that means it's a device that pumps heat out from the earth into the space. So this heat pump pumps 4 more units of energy out of the earth for a grand total of 5 units of energy. That's how, with the same amount of electricity, we get 17,000 BTUs of heat. So when you see these kind of things here, you go, oh, that's not even hard to figure out. That is obviously the way that we want to do this. Here's another reason why we want to do this. And as I travel around the world, I am seeing more and more of this going on. This is a New York apartment building that's one of the most handsome buildings I've ever seen with these air source heat pumps on it. And it's still beginning to look a little bit cumbersome, because you have all of these different brands, and all of them are freezing in the winter and going through the defrost cycle and having to drop this on top of each other, this ice and this condensation. In New York, I was very used to seeing this. Every time we had a major hurricane, the equipment would be blown about like blocks, and we would refasten them and put them down. But the bottom line is a lot of equipment gets blown off roofs, it gets damaged outside. On the other hand, you end up with unlicensed activity, or even worse, licensed. You see this, extended ladder here? I would not want to be the man working on this. This is craziness. What we're doing with a thermal energy network is we're bringing all the equipment inside where it needs to be. This is not sustainable. This is not what we want on our infrastructure. This is not a permanent solution, and it's really important that we see that now because it's getting out of hand fast. In addition to that, although air source heat pumps are amazing, I just have a bunch of slides here from the DOE that shows that you can't claim to have the same efficiency as a geothermal heat pump because you're dealing with thermodynamics, which means you have a greater source of heat. So in this, I wanted to point out that IATMO, who is firmly behind our efforts, a very, very focused entity on doing heating and cooling and everything about moving fluid the right way, they have worked very hard, and I started working with them on this in 2015. It's the first geothermal code for the industry. And we got that out in 2018, and then we got a huge geothermal section into the 2021 code. And now the ANSI CSA C448, which is a Canadian standard, which is accepted by IGSHPA, and IGSHPA is a co-sponsor of this, has several great chapters, and it's being updated right now on the geothermal installation standards for so many different things you wouldn't even believe it, including surface water energy transfer, closed loop transfer, aquifer-based thermal energy, and it goes on and on, even standing column wells and so forth. We were just a mechanical contractor minding our own business, and in about 2009, when Obama did the stimulus package, we got a call, and that's the bottom line is we got a call from McGraw-Hill, New York. So we wrote a book on geothermal, a very basic book on geothermal with about 15 chapters. And 3 years later, Greg Cuniff and myself and another man were asked to write a graduate level textbook, which we did. And that kind of put us to where we have been doing this kind of worldwide advocacy thing, which really started in earnest around 2013. And we've continued to work, and we've done children's books, and we've done a lot of educational efforts. So we continue on that, and we continue to write about the technology, and we continue to put information on this. Now, I'm going to talk some more about the thermal energy networks. So in the 20 minutes I have left, this is probably the most important thing to note. With a thermal energy network, which includes all of these single-family homes and industrial and resident and commercial applications, you can use all kinds of utility infrastructure. Now, I want you to wrap your head around this. There is a huge movement, though it is not yet readily accepted. There's a huge movement to use drinking water as an energy transfer medium, because we have to move just trillions of gallons of drinking water. And as a matter of fact, there's a precedent for this. And I just want you to think about this in the back of your mind. There's a precedent for this. In Ontario 17 years ago, Ontario, Canada, they needed to put in 3 deep water, drinking water sources from Lake Ontario. And they came up with this really good idea to do a 73,000 ton cooling loop, just transferring heat with the drinking water. So they literally, this is the way they do it. They bring the water in from Lake Ontario, treat it to drinking water standards, transfer the heat, get 73,000 tons of cooling, and then send it into the drinking water system. So that's drinking water energy exchange at its a very good example. And there are many, many other good examples like that. But I wanted to point that out because not only do we have aquifer thermal energy exchange and borehole thermal energy exchange, which is by far the most common and most well-engineered system. But we also have a tremendous amount of surface water energy exchange opportunity, and then this is to represent infrastructure. This represents both wastewater energy transfer, drinking water energy transfer, and what people don't think about is, especially in urban areas, dense urban areas, there's a tremendous amount of dewatering that goes on in almost every dense urban area, a tremendous amount of dewatering that just goes wasted, and that's a tremendous amount of energy, and we're finding that over and over again. So, and then you get into the places that are like Florida and probably here, irrigation water, gray water is a huge thing. We call it the water energy nexus because every time or every situation where you're moving a given amount of water is an opportunity for energy transfer. It's part of the water energy network. This is an example as we grow our thermal energy networks. This is an example of a 3-cluster university that uses 3 clusters of energy, totaling several thousand tons, and it has what this is called a central loop or a transportation loop that is able to transfer energy from one loop to the other as the load imbalances happen, and then whatever is left over in excess energy or needed energy is put to whatever heat source or heat sink we might have. So this is an example of just how far this is going. This is what we're seeing going into city centers. We have permission to share this, so we do. A lot of them are a little bit more sensitive. But this just gives an idea. This is an example. This is actually this drawing put in a more schematic, but this is how far this university is laid out in the clusters of buildings and how they were strategically put together. And as any good engineering firm knows, this represents probably several hundred hours of labor as engineers and technicians went through to audit all of the heating and cooling needs for the building. So one thing, what we really like to talk about when we do these sessions is up and coming technologies. One of the technologies that's really up and coming uses boreholes, but it has the opportunity to use an aquifer also, and it's called dynamic closed loop technology. And what you do is you're able to use the heat transfer, the advective heat transfer of an aquifer, but it has all of the components of a closed loop system, meaning that this is a pressurized closed loop here, and this is what we call a downhole energy exchanger. So what it does is it actually has a little submersible pump here, or if I say little, it's sufficiently sized submersible pump that forces advective flow of water through a downhole heat exchanger. And these heat exchangers are about 10 feet tall, and they're probably, we actually haven't installed one in the US yet. This is a Spain-based company, but they have thousands installed and a lot of great university papers, so it caught our interest, and it's something that we're investigating going further into. Anytime we're talking about an aquifer-based technology, that means that you have an abundant aquifer where you can pump from one well and inject to another. These are difficult systems because the aquifer may have a lot of impurities that can fall off in an exchanger, and it requires some specific engineering. So usually these systems are, even though it's shown for a house here, and many systems have operated in houses for decades, for generations, still, if it's not a good quality water, we find that most of these systems engineered are several hundred tons, and usually a commercial system that has a regular maintenance protocol because there's so much going on with that. So that's an aquifer-based system. This is like an aquifer-based system, meaning this is a closed loop, but down here this exchanger is moving a lot of groundwater through it. So it provides up to 30 tons of heat exchange per borehole. So it's a marvelous technology, and it satisfies a lot of grief you get from people, AHJs we call them, authorities having jurisdiction, that don't like you pumping water out of the ground. They like the closed loop technology. This really helps to satisfy that. And so we've seen a lot of forward movement from that. There's other technologies called direct expansion, where most technologies, we use a water-based solution through a heat exchanger like this. A direct expansion system actually runs refrigerant outside and into the ground. And that's actually covered in CSA 448 also. They look like this. They actually are refrigerant lines, and they usually have a small footprint. I wanted to focus a little bit on something that's a huge issue right now. In case you don't know it, it's not the case in Atlanta probably. It is a little bit the case in Florida. It's a lot the case in any desert Southwest area. Drought. Drought is becoming a huge issue. And as a matter of fact, in Nevada, by 2024, they have indicated that evaporative cooling will no longer be allowed. Everything will have to be dry cooling, and everything will have to be, everything will have a much higher, unless it's a geothermal source, it'll have a much higher condensing temperature. So one of the things most people don't realize with regard to evaporative cooling is it's the third highest consumer of energy in the United States. Agriculture is always number one. Drinking water and that type of thing, restroom facilities, number two. But evaporative cooling is far more than most people even think. It is beyond my comprehension to realize how much water you can use from evaporative cooling. Now, with the advent of data centers, this has become massively interesting. Now, I'll give you an example. There was a Facebook data center that was announced 2 years ago for Arizona, near Phoenix, and they caught serious backlash, and I can understand why. One data center was slated to use more than 1 million gallons of water a day in evaporation and blowdown. That is a lot of water when you're considering that you're a drought-stricken area. So a couple of ways to deal with that. Both of them involved piped infrastructure, but this is a project that we got involved with, and we're seeing a lot. This is common sense, but it just isn't pictorialized very often. This particular project, which is a 120 megawatt project in the mountains of Wyoming at 7,000 feet, they created a user of their heat. They created, in Wyoming, they don't have a crop because they don't have 4 seasons, not at this elevation. So they decided to take a little bit of the load off of Southern California and pulling in all those fresh fruits and vegetables and create a multi-hundred acre Wyoming hyperscale indoor farms. So this is not novel, it's not new, it's something we always have known we need to do, but it doesn't seem to happen in a big way very often. And so we need to see more of that happen. Data center variations for source and sink, which data centers are becoming more a part of our life than ever. You can go with the standard dry cooler, evaporative cooler. You can go with a closed loop system. You can go with an aquifer thermal exchange system. You can go with a combination of these. You can use a heat off taker, like we mentioned with the farms there. Geothermal infrastructure belongs to our mechanical trades, and that's what we're focused on here. We want to keep our mechanical trades working. There are 3 decades of work ahead just on work that we see coming up. We want to allow utilities for BTUs and give them a path to become renewable energy companies. We're trying to be able to encompass all of the opportunities for heat exchange that are possible. One of those that I haven't focused on a lot today in balancing our energy budget, everybody's heard of an energy recovery ventilator, right? So energy recovery ventilator simply means that there's a certain amount of fresh air required for every building. An energy recovery ventilator is required in a lot of jurisdictions by code because the amount of air-conditioned or heated air you have to exhaust should be exchanged with some of the fresh air coming in to save some BTUs and save some energy. One of the things that is the biggest decarbonization, low-hanging fruit opportunity around is wastewater energy transfer. It's been shortened to an acronym, WET, W-E-T, and wastewater energy transfer has a lot of traction, really worldwide, but nationwide especially. We're noticing a lot of projects getting funded by multifamily condominium complexes, especially high rises and so forth, because a lot of times they'll have a common wastewater pipe coming down through the building. And by putting one, it's really a few components, but it's really one system. It's basically a wastewater energy transfer system like I talked about. They're able to create enough heat or recover enough heat from their wastewater to do all of their domestic hot water heating and cooling using electric heat pumps, once again, and a special wastewater energy transfer apparatus. So this has become a huge opportunity to decarbonize and start facilities off on the process of decarbonizing at least their domestic hot water. Now, where it's really starting to gain some traction is a combination of wastewater energy transfer and geothermal, because a wastewater energy transfer and geothermal system can reduce your geothermal exchange or your geothermal exchanger size by about 40%. That's a claimed average by the manufacturer of the wastewater systems. So by using wastewater energy transfer, a little bit of thermal energy storage, a lot of this is seasonal and can be done, much of it can be done as part of a thermal energy network. By using surface water energy transfer, which we shorten to SWET, surface water energy transfer, data center energy recovery, we can provide plenty of heat to decarbonize our residential and multifamily buildings. We can provide plenty of energy transfer to do our apartment buildings, our office buildings, and as I said, we'll always end up with a little bit of extra energy. There are technologies coming together that can use low-grade energy to create electricity and other useful things. So we are waiting for those to develop as we go. And so I'm going to go ahead and leave it there and see if there are any more questions. I like this one here because it very simply shows that if one place needs to be cool, one heat pump is pumping heat out of the water into the ground loop. Another place needs to be hot. Another heat pump is pumping heat out of the ground loop and into the surface. You get what we call thermal energy transfer between the two, and you end up taking two heat pumps that have 3, 4, or 5 COP, and the resultant COP is about 9 or 10. And so you exponentially increase your efficiency by sharing heat from one system to another. I'll leave that with you, thankfully, and leave it open for any questions. Thank you.
So municipalities own the infrastructure. They're going to have to create the billing mechanism to actually make it function, correct?
Yes, and that is actually, I would invite anybody else to say anything about it, but yes, it is actually, if it's being done with ESCOs, energy service companies, it's easy because they make a mechanism to do it. But when you get into municipalities and utilities, they have to have something that's passed by the city council. They have to have something that's passed by the Public Service Commission. So that all that's being ferreted out this year and next year, and what I'm seeing anyway.
Is there opportunity with water through large-scale irrigation like golf courses? You alluded to that.
Yep.
Prior to the being put in, but a golf course still has, they're watering all the time if you go south.
Yes, exactly. And one of the things we're going to look back on, just like we look back on a lot of silly things we do now, but we're going to look back on it and realize just how much energy opportunity that we have that's just going out without being captured. But golf courses are huge. Any wastewater, I'm sorry, any the type of water I'm looking for is the non-potable water that they use for irrigation. I just lost the name of it in my head. But those type of, anywhere you have fluid moving, especially golf courses, and think about this, wastewater, when you have wastewater treatment plants, they have the effluent that's just normally being pumped into the rivers or down into aquifer recharge wells. All that should be thermal energy transfer, and it will be. It's a great question. I really appreciate it. You're starting to see the vision of it. Yes, sir.
Hi, thank you so much for the presentation. I wondered regarding this slide, why in summer they are pretty close.
I have often wondered that, and I think that's a little bit flawed. I've seen a lot better performance in the summertime than that, but it's the slide that it's an official slide from the ASHRAE report, and it's the one we chose to use probably because it had such a bad winter in 2010.
I can answer some of that for you.
Oh, thank you, Rick.
Yeah, part of it is that because this was the ASHRAE headquarters building, which it's not now, the loops were sized pretty tight. What happened is that the average temperature that the ground loop ran in the summer was 79 degrees. The average temperature for Atlanta that summer was also 79 degrees. It was a coincidence, but that's why they were as close. The biggest part of this whole thing is that winter differential is in Atlanta. We're in Atlanta. I don't know where you've come from to get here, but where I came from, I didn't come from San Diego like she did, but that's why.
I never knew that. Thank you, Rick. What did I tell you? This is a geothermal encyclopedia. Thank you.
50 years, that's why.
Yeah. That was a great question and an even better answer. Thank you.
You mentioned that the loop temperature was 79, so what's the average loop temperature? I thought it would be down in the 50s or so.
Well, the loop temperatures are designed for a range, and normally budgets affect, so there's really good software now that looks at the loads and looks at the weather and the profile for the buildings, and if they've run Energy Plus or on the building, they know exactly what's going on. That software can then say, we're going to let the ground loop maximum temperature be something, 90 typically, not go up below 40. You're trying to make it so it's going to operate in a range. So when that building was so well metered that we knew all over the whole summer that it averaged 79 degrees. And part of that, remember, there's got to be a differential for heat to move. So that's why it was that temperature.
Yeah, there's always. That's right.
ASHRAE, just look at it like this. Why was the ground source system on the second floor and the VRF system on the first floor?
Right. Yeah, I thought about that too.
Because it wasn't going to be compared to Geo. VRF was going to be compared to rooftop.
I did not even know that. See? That's amazing. Courtney, do you have a comment or a question?
I have a question. So as we're starting to look at these thermal energy networks and utilities are able to sell the thermal energy, how are they going to meter it?
That is a great question. And we were just in New York with Con Ed on Friday. And we don't know whether they're going to do BTUs in and out, BTUs out, GPMs. There's a whole lot in flux about that, but it's being decided, at least in New York, very quickly because the information is going straight to the PSC and they'll write standards based on that. So we will definitely be needing input on that as we move forward. Thank you. Yes?
Probably if they install heat pump on the network and the performance of the heat pump at that temperature is quite based on the performance curve, then they measure power of the heat pump and translate it to the heat that they exchange with the network.
That's another way. You never, yeah, and that's a lot of hocus pocus, but it might be.
The most important regulated way to measure BTUs in and out of the building is GPM and delta T.
Yes, sir.
Every one of these buildings can be measured GPM delta T. You know exactly what's going on, and it's great for the utilities when they have to do a critical analysis. What's the benefit analysis for this system? Here it is.
In Miami, where they sell chilled water, Florida Power and Light, that's how they measure it. They measure GPM and the temperature.
Ah,
Because sometimes their freeze tanks haven't regenerated as well in the summertime, so their water's a little warmer, so you get a lesser charge. But when it gets down and it's 40-degree water coming in, you're getting premium charge.
wow.
GPM.
So you have some knowledge of what's going on down there in Miami, huh?
Well, that's 10 years ago.
10 years ago, got it.
Water in building. Every major building has got condenser water loops and individually on them, units that 4x4, cut 10 by 10. They're built for condenser water.
And most Florida buildings are that way with a water tower up on the roof.
Yeah. By the way, this, I'm very easy to get to. Just Google Egg Geo and send it to info. I will send anybody that wants it a copy of this PowerPoint. And would love to help anyway, and I'll be here for a little while if anybody wants to share any cards with me.